Hello, in this short video I'm going to solve the following problem for you. In a group G with identity element E, for any elements A and B in G, we have AB squared equals to BA squared. Additionally, for every A in G, if A squared equals E, then A equals E. Prove that G is abelian. Pause the video at this point and give it a try. Okay, so I know these two conditions. Using these properties, I want to show that the group is abelian. Okay, I start with a lemma or a claim. So what is that claim? My claim is that if you give me alpha and beta in the group G, then alpha, beta, alpha inverse becomes equal to alpha inverse, beta, alpha. It means that if I have alpha and alpha inverse, one element and its inverse sitting on both sides of another element, those elements which come in pair, alpha, alpha inverse, they can be reversed. So alpha inverse can be put first. Okay, to prove this claim, I look at the second power of this combination, beta, alpha, beta inverse, squared, in two different ways. One way is the normal way. It means that I take the element and multiply it by itself. Yes? And of course this one is just simply the identity element, so I can ignore that. Alpha alpha becomes alpha squared, so it becomes beta alpha squared, beta inverse. Another way that I want to calculate this, I want somehow exploit the property given in the problem. I will look into beta and alpha as one element. I group them together and then I have beta inverse. Then I have its second power. Now I want to use this property by giving the role of A to this expression and giving the role of B to beta inverse. What do I have? I have AB to the second power. So AB to the second power can be written as BA to the second power. So this becomes beta inverse multiplied by beta alpha to the second power. But then beta inverse beta can be grouped together using associativity, and it gives me identity element. Identity element times alpha is alpha, so it becomes alpha squared. So you see, I calculated the same expression in two different ways. One of them gave me this answer, the other one gave me this answer. So evidently, these two answers should be the same. So beta alpha squared, beta inverse should be equal to alpha squared. Now what I do, from the right hand side, I multiply both sides by beta. So the left hand side becomes simply beta alpha squared, and the right hand side becomes alpha squared beta. So this is a result that I want to use it. Okay, now I start from the left hand side of the claim that I made. So the left hand side of the claim, which is alpha, beta, alpha inverse, can be written as, instead of alpha, I can write alpha inverse, alpha squared. It gives me the same as alpha, and then I copy and paste the rest, meaning beta, alpha inverse. Why I did this? Because now this combination, alpha squared beta, is exactly equal to the right hand side of this expression, so I can replace it with beta alpha squared. So I copy and paste alpha inverse on the left and alpha inverse on the right, and instead of alpha squared beta, I can simply put beta alpha squared. But then this alpha squared and alpha inverse becomes alpha, and I will get alpha inverse beta alpha, and that is equal to the right hand side of my claim. Now I want to prove the group is abelian. What does it mean? It means that for every pair of group elements like x and y, I want to prove that xy is equal to yx. So this is my goal. Now I look at this combination, xy, x inverse, y inverse squared. Okay? Of course, an element to power 2 means that element multiplied by itself. Okay? But now you see this combination x, y, x inverse is the same combination in my claim. So it means that I can replace x at an x inverse. So this becomes x inverse y x y inverse. And I just copy and paste the content of the second pair of brackets. But now this one has the same structure as you see here. Yes, y x y inverse. So I can interchange y and y inverse. So it becomes x inverse y inverse x y. And again, I copy and paste the content of the second pair of brackets. But now you see xy appears here and there, so it becomes simply xy to the power of 2. And this is a famous group theorem, so I can write it as yx inverse. And the same story here. This becomes yx inverse. But what do I see? I can go back here and use this property once more. I have xy second power. If I have a second power, I can commute the elements. So I can commute these two. So then it becomes yx inverse yx squared yx inverse. And hopefully you agree with me, this is e. Because this inverse cancels one of these powers, the other inverse cancels the next power. So I will get e. So what I did, I proved that xy, x inverse, y inverse to the second power is e. But now I exploit this property. This property tells that if you have a group element squared, which is the identity element, then it means that the group element itself is the identity element. So I have a group element squared is e, so I can conclude that xy, x inverse, y inverse is e. I multiply both sides by y from the right hand side, so it gives me xy, x inverse equals to y. And again, I multiply both sides by x from right, so it becomes xy equals to yx. So this means that my group is abelian. So I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.